Okay, so let's consider a graph. Okay, so I'm going to show you a graph. So let's pull up a graph. Okay, and I'm going to label the vertices. So here's V1. Here is V2. Here is V3. Here is V4. Here is V5. So V5. And here is V6. Okay, and I'll draw the graph a second time. V1, V2, V3, V4, V5, V6. Okay. And well, those are just the vertices. Now let me tell you what are the edges. Okay, so this guy's connected to those guys. This guy's connected to those guys, and this guy's connected to those guys. Okay. I'll draw it. I've drawn it twice, just to illustrate something interesting. Okay, so same graph drawn twice. So now what I'm going to describe for you is what's called the greedy coloring strategy. So greedy. Okay. So let's number our colors. So our colors are 1, 2, 3, 4, and so on. Okay, and because we do actually have colors, let's call the first color blue. Okay, the second color red. The third color green. Well, actually they're just numbers, but we can call them blue, red, green, and let's say black. Okay. Now the greedy algorithm works as follows. Okay, we start from vertex V1 and then we go V2, V3, and so on. So we increase the vertices. And whenever it's time to color a vertex, color that vertex with the cheapest, the smallest, i.e. the smallest number color that you can. So when we start with V1, nothing else is, you'll see how this works. So I can color V1 with blue. That's the smallest number color that I can. Okay, good. So I've colored V1 with blue. Now I come to V2. So what color can I give V2? Well, I can give V2 also blue. Okay, because it has no neighbors that are currently colored. So V2 I can give blue. Okay, now let's talk about V3. Well, V3 cannot get the color blue because it's got a neighbor that's already colored blue. So the smallest color that V3 can get is red. So we give it red. Okay. Now we come to V4. V4 also cannot get the color blue. Okay, because V4 is got a neighbor who's colored blue. So the smallest color that V4 can get is also red. So this is red. Okay. But now this is interesting. Now when I come to V5, V5 cannot get blue. It cannot get red because it's got a blue neighbor and a red neighbor, but it can get green. So we can color this guy green. Okay. And now that we've colored this guy green, we've done V5. Now we come to V6. V6 cannot get blue, cannot get red, cannot get green, cannot get blue, red, or green. So the smallest color it can get is black. And there you have it. Okay, there you have it. A coloring, and we used 4 colors. 4 colors. So this notion of giving the smallest color to a vertex and is what makes this algorithm greedy. And as you can see, we have a valid coloring because at every step when we color a vertex, we always give it a color that doesn't conflict with any previously colored vertex. Okay, so it guarantees that the coloring is valid. But is it optimal? Nowhere close. Okay, we used 4 colors. Okay, to get a valid coloring. I claim you can do it with just 2 colors. Here, I'm going to give this guy blue, and this guy blue. Okay, and then I'm going to give these guys red, and red. Okay, and now I've done it with just 2 colors. Okay, so the problem with greedy is that, it may use more colors than necessary. It always guarantees that you get a valid coloring. And then you might think, why did we choose greedy? Why did we do that? Because we don't know of an algorithm that can efficiently color with the minimum number of colors. So we don't know how to efficiently color with the number of colors. So such a simple problem that even a 3-year-old could understand it. I could give them this graph and say, go color, and they'll easily come up with a way to color it with two colors. I can give it to a 3-year-old, a 5-year-old, a 6-year-old, whatever you want. But if I give this problem in its general form to a mature 25-year-old, we cannot do it efficiently. Bam! And we see that in order to resolve conflicts, we need to be able to color. So it's an important algorithmic challenge that involves graphs. Okay. Let me show you that trees can always be two-colored. By the way, from this algorithm, you can see that whenever it's time to color a vertex, at most all its neighbors have been colored. Okay, and so that if it has degree delta, then delta colors have been used, and so you'll never have to color a vertex with a color higher than its degree +1. Okay, so this algorithm shows that you will never color a vertex with a color larger than degree +1. So that means that it's always possible to get a valid coloring of a graph with a number of colors that's equal to the maximum degree +1. That's always possible. And that coloring is easy to do with greedy. Okay, but how to get the minimum number of colors, we don't know. Okay, let me show you that trees, and in general, but I'll just show it for rooted binary trees, can always be two-colored. Rooted binary trees are two-colorable. Okay, and the base case is trivial with the epsilon. So I'm going to use structural induction, and the basic idea here is that I just need to show that if the parents are two colorable, then the constructor rule preserves that the child is two colorable. That's structural induction. So let's take two parents. Okay, and let us assume that they're both two colorable. Okay, so for the root. So two colorable means that you have given, let's say, two colors to the vertices, let's say red and blue. So let's assume that this guy got blue, okay, for the first vertex, and then whatever inside, maybe there's some blues and some reds, but any blue is not connected to another blue. So, maybe this is connected to a red up here and so on. Okay, now we can connect this guy. And then, maybe red, and then so on. So we've got a tree here, and we've colored the root blue. Okay. Now, supposing we've also two-colored this tree, which is assumed because they're both going to be parents. Okay. So, what could happen is that we've colored this root red, okay, and then, maybe blue here, and then red here, and so on. Okay, so these are the links. Okay, and so on. Okay. Now, I would like it instead to be the case that I've colored this guy with blue up there. And can I be always sure of that? Yes, because I can just relabel the colors, flip the colors. Wherever I use red, use blue, and wherever I use blue, use red. So here I can make this blue, and this blue, and I can make these red. Okay, I can just flip the colors. In doing this, I can always ensure that these two roots have been colored the same color. And these two parents are two colorable, with the roots being the same color. Okay, so remember where I'm going. I've assumed that the parents are two colorable. I want to show that the constructor preserves two colorability. Okay, so here I've got a two coloring of the parent with a blue root, and I'm going to request that whatever coloring you give me for the second parent also must have a blue root. And I know it's two colorable, and if you need red here, then let me flip the colors and get blue here. Okay, but now what does the constructor do? The constructor takes these two roots, okay, and connects them to a new root. I claim that this tree is two colorable, and here's the proof. I'm just going to color this red. Bam! I've colored the child that was produced, because look, this child red is connected only to blue nodes, and then these two were two colorable, so I haven't changed anything in there. And so these are valid two colorings of the parents, and with this guy being red, with this vertex being red, I've got a 2 coloring of the child. So, the constructor for RBT preserves 2 colorability. And that's all I need to prove for the structural induction, in addition to the base cases, but the base cases are easy to verify. Okay. So I just proved that if the parents are 2 colorable, then the child is 2 colorable. Therefore, every RBT is 2 colorable. And effectively, you can see this as follows. So here is an RBT. Okay. Basically, what's going on is an RBT has levels, and effectively, I'm coloring every other level 1 color, and every, in between level, the other color. And now you can easily verify that this is a valid coloring. No edge connects 2 nodes, 2 vertices of the same color. Okay, so that's coloring. Very important for conflict resolution. Trees can be 2 colored, and there's an efficient greedy algorithm that gets you a coloring that uses at most the maximum degree plus 1 colors. And we use coloring a lot for conflict resolution. Let me show you a whirlwind tour of other graph problems. Okay, other graph problems.